The disease that I chose for the portfolio milestone assignment was Tay-Sachs disease, which is what I will be doing my presentation on. So the history of Tay-Sachs disease. Tay-Sachs disease is a rare disease that is inherited due to the genetic makeup of parents passing on the gene to their children. Tay-Sachs specifically is a lipid metabolism disorder. And a lipid metabolism disorder affects the way that your body breaks down lipids, and that you might not have enough enzymes, specifically the enzyme hexosaminidase A, to break them down. Lipids are important in the food, in that food is made up of proteins, carbohydrates, and fats, which are also lipids. Having a lipid metabolism disorder like Tay-Sachs can affect and even damage cells, tissues, liver, spleen, bone marrow, brain, and the peripheral nervous system. Tay-Sachs is most commonly found in Eastern European Jews, but anyone can be a carrier. According to an article that I found throughout my research, approximately 1 in every 27 Jews in the United States is a carrier of the Tay-Sachs disease gene. Non-Jewish French Canadians living near the St. Lawrence River and the Cajun community of Louisiana also have a higher incidence of Tay-Sachs disease. The general population has a ratio of about 1 in 250 people are carriers of the disease. So, physical effects of Tay-Sachs. It affects infants, and most children born with Tay-Sachs only live to about 3 to 5 years old. Children born with the disease appear to develop normally in the first few months and then start to show a physical and mental decline. Muscles start to become affected and waste away, causing blindness, deafness, and the inability to swallow, which ultimately leads to the death of most children. There is no cure or treatment for Tay-Sachs other than treating the symptoms of it. Researchers are, though, trying to find and use different approaches to finding a cure. One of those things that they have tried is using enzyme therapy, and it provides the hexa-A enzyme that is lacking in the infants. And a second approach is bone marrow transplantation, which unfortunately hasn't been successful. And the approach that seems to hold the most promise at this time is gene therapy, which transfers a normal gene into the cells to replace the abnormal gene that causes this disorder. So the responsible gene for Tay-Sachs disease is hexa-A, and it is located on the chromosome 15. Enzyme B hexosaminidase A, or hexa-A, as the alpha subunit of hexa-A, encodes for on chromosome 15. The normal function of the subunit enzyme is to degrade a lipid called GM2 ganglioside, but when an individual has Tay-Sachs, there either is very reduced amounts of the enzyme or it's not present at all. This then leads to the buildup of GM2 ganglioside in neurons. The buildup then affects many different parts of the body and their functions, which was mentioned earlier in the presentation. So this is an image of the genome data viewer, and it shows, you can see hexa A, which is right here, and then the other genes that are next to hexa A as well. So this just gives you an overview of the chromosome that hexa A is located on. Hexa A, so the gene encodes a member of the glycose hydrolase 20 family of proteins. The encoded pre-protein is processed to generate the alpha subunit of the lysosomal enzyme beta hexosaminidase. Mutations on this gene lead to an accumulation of GM2 ganglioside in neurons, and the underlying cause of neurodegenerative disorders termed the GM2 gangliosides, including Tay-Sachs disease. So this is the reason behind neurodegenerative disorders. Alternative splicing results in multiple transcript variants, at least one of which encodes a pre-protein that is proteotypically processed. So the mode of inheritance for Tay-Sachs disease is autosomal recessive pattern. So some of the images down below show you how that works. If you are a carrier, then if two carriers come together and have a child, they have an increased chance of their children having Tay-Sachs disease. And the image down below is a good visual showing how that works. An autosomal recessive pattern means both copies of the gene in each cell have variants. This means specifically that the parents of a child carry one copy of the affected gene. So the man here has a copy of the affected gene, and the female carrier has a copy of the affected gene. So that's what carrier means. Carriers also have the gene, but that means that they don't show symptoms, so you don't really know if you're a carrier for it unless you get tested. Tay-Sachs is also considered a lethal allele genetic disorder because of its mode of inheritance. If two people who carry it have a child, there's a 25% chance that the child won't inherit any faulty genes and won't have Tay-Sachs. There's a 50% chance that the child inherits a faulty gene from one parent and becomes a carrier but won't have any of the symptoms or the condition themselves. And then there is a 25% chance the child inherits the faulty gene and develops Tay-Sachs disease. So this is an image of the pedigree that I created for Tay-Sachs. This is just an example of what it might look like. The red are the affected who possess the gene for Tay-Sachs disease, and because it affects young children, they all died at a young age. So genetic testing for Tay-Sachs disease can be as simple as a blood test to identify the carriers. Blood samples can be tested either by an enzyme assay or DNA studies. An enzyme assay is a test that measures the level of hexa A, which is the gene that holds Tay-Sachs disease. And DNA studies test looks for the mutations or changes in hexa A. Testing is optional. It's not mandatory. If someone of the descent that is commonly affected by this disease wants to get tested before they decide to have a child to see if their child could potentially have Tay-Sachs, it's completely optional. It's not mandatory to do that. The age for genetic testing varies if the testers are adults, and like I said, want to find out if they're carriers, they can do the blood test or the DNA studies at any time. Prenatal testing is available and can be performed at about 11 weeks of pregnancy. The prenatal testing is done using chorionic villi sampling, and it removes a small piece of the placenta. Otherwise, another option for prenatal testing can be completed by an amniocentesis, which is around 16 weeks of pregnancy. Early detection is important just in the circumstance that parents of a child have or are carriers of Tay-Sachs disease. Then they can test either their child or themselves to find out if they will be affected by the disease or their child will be affected by the disease. And then that allows them to prepare and or handle the results that they might find if they are carriers or their child has it. The typical cost for genetic testing is about $149 with private insurance and $349 without insurance. Blood testing, so that's for the DNA studies because it's as simple as a saliva sample. Blood testing can range from $50 to $1,000 depending on insurance coverage and location. For the chronic villi sampling, which is a prenatal test, the cost averages around $3,000, and the cost for an amniocentesis costs anywhere between $1,000 to $7,000, depending on the insurance coverage and location as well. The only controversy that's associated with testing is just how handling the results that two carriers might find out if they potentially carry Tay-Sachs disease and they want to decide to either continue with the pregnancy or decide to have an abortion because they don't want their child to go through and end up passing away anyways from the disease because there's no cure. So that's the only controversy that I could find. So that is it for my presentation on Tay-Sachs disease. And these are the sources that I used throughout the presentation. Thank you for watching.